So it's a very great pleasure to introduce to the Social Simulation Week community Anima Anandkumar from Caltech University in California. And Anima I'm very happy. I'm privileged to introduce Anima today. And I'm very happy because I decided deliberately to contact you and to have you in this kind of community because I've seen a lot of connections between what you are doing, the amazing job you're doing, and especially try to explore and improve, extend machine learning and using especially simulation to train algorithms on simulated data instead of on empirical data, which is a great idea. And I do believe there's a lot of potential connections between what you are doing and what we do in our community in terms of developing models which simulate agent behavior and generate artificial data to try to understand a little bit the complexity mechanism of our social system. So, and I also happy and I also like your path in the sense that you are crossing academia and industry and different kind of words, and it seems to me that you are doing an incredible job in bridging and integrating this kind of words. And so I'm very happy and I'm privileged to introduce you, as I say, and I'm very happy that you accepted, agree to give this this talk, although you're a very busy schedule. And I'm very happy to listen to your talk, and our colleagues will surely also be happy like me. So, Anima, you have 45 minutes for your talk. I will help you, and I will take care of the chat in case someone. But in case you have any question, please use the chat. I will monitor the chat, and so that Anima can give her presentation without being interrupted, or if you prefer to be interrupted, it's up to you. And I will help you to manage time, and at some point, whenever we jump into 45 minutes, I will try to help you and to at least to notify you that we are just running out of time. But take your time. We are here to listen to you. Thank you very much for accepting our invitation.
Thank you, Flaminio, and for including me and introducing me to this community. That is a lot I want to learn, and I was looking at the program, and I think, like I was telling you just a few minutes earlier, modeling human behavior is such an important problem in the current age, right? Especially when we see social media having a lot of bad effects on society. It's important then we ask, how we can model human behavior well and get good outcomes from human interaction, whether it's in social media or other avenues. And I think it's also important for me as an AI researcher to think about this, because ultimately when we are designing embodied AI, that is robots that are intelligent agents, they need to interact with humans. So it's important to understand how humans are going to behave and interact and make that much more seamless. And we are in a very early days when it comes to that, right? So a lot of my talk will be about general AI principles, what it takes to have generalizable AI that goes beyond the current regime of supervised deep learning. And hopefully some machine learning principles are also useful to the social simulation community, because principles like discovering causality, being able to generalize under domain shifts, making use of good simulations and combining that with real data, I think those are also applicable to researchers in this community. But I'll talk about how we've been using that when it comes to designing learnable robots and in many other applications. So that'll be an overview, and it'll be work done both some of that in NVIDIA research and some of the work done at Caltech. So as you know, AI has been so much in the news and has given us so many impressive gains, right? The AlphaGo beating the human champion in the Go game was unprecedented, and now we also have NVIDIA GANs generating photorealistic images. So all these images are not a real person, right? And it's very hard and surprising for people to kind of wrap their head around the fact that you can generate such photorealistic images that pass the Turing test. So there's lots of impressive growth in AI with deep learning, but there are also, sometimes it just kind of, let me, yeah. Sorry, it was stuck for a second. Yeah, but there are also lots of hard challenges, right? I mean, self-driving cars, we've been now talking about it for more than a few years, but it's nowhere ready to be on roads with widespread use. And the reason is because these are safety critical systems, meaning even if you're right most of the time, there's a long tail and you have to be able to account for all kinds of situations, right? So, and it's also really important because human lives are at stake. This is the sad fatal accident by Tesla Autopilot when it just went straight into a concrete wall. So these are all situations we have to be so careful about and design now a new foundation for AI to handle such challenging applications. And indeed, when it comes to the state of robotics today, most robots have no intelligence. So the Boston Dynamics Atlas robot may do the impressive backflip, and the dog may just fumble and not always catch the ball, but the dog is so much more intelligent than the robot, right? The Atlas robot, in fact, is programmed, so it has no intelligence. It can't adapt to any new situation than what is staged there. And even though that's an impressive aspect from control systems perspective, from the AI perspective, it isn't, right? Because there is no intelligence. And so if you want to like ask what is the path to embodied AI, so that is the melding of mind and body coming together. So we have the robotics and AI methods coming together. We need to incorporate a lot of human intelligence. You know, humans are instinctive, right? We kind of have good representations of the world around us, even though we can't explain why, we have the instincts that lead us to making hopefully good decisions many times. And I'm sure in this community, that's something that's also well studied. And then humans are deliberative, right? Like we make and adapt plans. We can also make long-term plans and short-term plans and look at multiple timescales in interesting ways. And, you know, we also have a reasonable sense of safety. You know, except the teenagers, once the human brain is evolved, the hope is, you know, we can assess risks well. I mean, we know not to jump off from a too high a cliff. So we have an understanding of what it is to ensure safety. And the current robots don't, right? So you can have these navigating robots just go off and veer off a cliff because they made a wrong decision. And then the most important aspect, and that's something this community studies a lot, is the multi-agent behavior. You know, humans are social beings, and they can coordinate, they can compete, and these are aspects that is still missing in robotics and is very much in its infancy. So the role of interaction is an important one that's needs to be developed. And this slide, I want to give a sense of what has created this deep learning revolution, and now to take it to the next level to create embodied AI, what new ingredients should we add, right? You know, I kept saying deep learning, so, you know, there's a lot of emphasis on algorithms all the time, right? When you talk about AI, right, an algorithm comes to your mind. But what's important is the role of also data and compute infrastructure. So that's also critical to look at these other two facets. It was, in fact, the creation of ImageNet by Professor Fei-Fei Li at Stanford and the Caltech alum that started the deep learning revolution. Because without millions of labeled examples, you couldn't harness the power of deep neural network. And the compute infrastructure was also critical. We were able to use the NVIDIA GPUs because of the parallelism and parallel matrix operations, and able to learn at this large scale. So this confluence or trinity of data, algorithms, and compute infrastructure has created the deep learning revolution. And that's why if we want to now proceed further, we want to ask, in all these facets, how do we enable further progress? So I want to break down any AI algorithm into 3 parts, right? And see how we can now further enhance the current crop of supervised deep learning methods. So if you look at an AI method, of course, it needs to learn from data. So what kinds of data sources is available to this algorithm? That's important to look at. The other aspect that is not so emphasized in deep learning, but is very much so in statistics and classical machine learning, is the role of priors, right? What kind of priors do we have available? What kind of domain knowledge do we have? And how to incorporate that into learning. So this is the learning aspect, but then there's also the decision making, right? So if you're not just learning passively from a fixed data set, but actively interacting with an environment, there's also the action you need to take. And that's called usually reinforcement learning, or right, active learning. All these are examples of where there is this decision making to be done. And so this combination is what makes an AI algorithm. And if you look at standard deep learning methods, they're usually extremely data hungry, right? And most of the methods are supervised methods, meaning we need human labeling, and this is expensive and in some areas maybe impossible to get at scale. So that's a limitation. When it comes to priors, again, we have very weak priors in our current deep learning methods. If it's images, we may do convolution and that's about it, right? So the question is, can we make it much more domain specific? And I think this is critical for robustness. If you can't have good priors, you can't expect a robust method, right? So, and a robust method that would also be very accurate and performing on complex domains like images. So the question is, what kind of priors can we embed? And this is an example here of famous kind of, there are many examples like this where you can just put some blocks here, right? And a human can still easily tell that this is a stop sign, but current AI methods can't, right? It completely changes what it thinks is in the image. And this is dangerous for self-driving. So that's why the current AI methods are not ready for challenging applications like self-driving. So the question is, how do we build better priors? So I won't give all the examples of it in this talk. We also have done some recent work looking at inspiration from the human brain and how in the visual cortex and IT cortex in the human brain, we have feedback mechanisms, whereas the current deep neural networks are only feed forward. And so we've also designed new architectures with feedback that has better robustness. So that's an example of a better prior than what current deep neural networks have. But I won't be going into the details in this talk, but you can go into my website if you want to learn more about that. And then the last part is the design of the task, right? This is also a limitation with the current methods because the benchmarks are limited and fixed. So even with ImageNet, right, we've reached the limit because it surpassed human ability on ImageNet. So this means we've overfitted to the data set, and we need to go to even much larger scale ones. So there's always going to be not enough data if we are limiting the benchmark. On the other hand, in the real world, it's an open universe, right? So you may encounter any new scenario like we've seen with self-driving cars, if they're on roads. So we need to be designing benchmarks that are not so limiting. And this is not only a performance issue, but also a fairness issue. A famous example is face recognition and facial analysis. This is very controversial and for good reasons, because currently most of the data sets are heavily imbalanced and have very small amount of darker skin tone people. Because they've been built on the history of celebrity data set, which is easy to take from the web, and that's predominantly white and also right, the women wear makeup. So there's lots of biases in these data sets that are created. And now if you put this out in the real world, that's also a dangerous thing, because even famous Black celebrities like Oprah Winfrey, right, could be misgendered or misclassified, like we've seen in some of the examples of public APIs. And so it's important to think about how we are going to design our benchmarks, what data do we test on, and how is it going to be used in the real world. Especially if facial recognition is used by law enforcement, that can be a life or death situation, and that can amplify the societal biases even more. So it's important to think from all these different lenses to design the right task. And I feel like currently the community is not doing enough of that, and we're just barely starting to think about this. And so this is the status quo, and then the question is, where do we go from here? What is this path to generalizable AI? And on each of these aspects, how do we handle data better? What kind of new priors do we create? What kind of tasks do we design? So all these aspects, how do we do better? And that's where I think there are some high-level principles we can adopt. This is like the wish list, right? So what we would like to have is much more innovation in unsupervised learning. So moving beyond just optimizing for accuracy on a labeled data set, can we go and discover new concepts? Can we disentangle different factors of variations without or with very little supervision? Can we also reason with the concepts, right? For instance, humans can do zero-shot learning. For instance, a child which has never seen an elephant, when it sees for the first time, will still know it's an animal, will still know that it can walk, it has eyes. So all these are aspects that humans just intuitively know, but very difficult for the current methods to do well, because it's fitting on certain features of the data in a supervised way and not learning the underlying concepts of what makes an animal. And that's what we'd like to change and ask, can we design better benchmarks for learning concepts? And we'll be soon releasing an interesting challenge along this direction, so stay tuned. I can't say any more at this point. But I will be talking towards the later part of this talk on disentanglement learning and what are some good principles to have disentanglement. And then the second thread, as I mentioned in the previous slide, getting good priors, like taking inspiration from how human brain processes information through feedback, and looking at other kinds of domain knowledge is interesting. So especially on, in my Caltech role, we've been looking at a lot of AI for science problems, right? I co-founded a campus-wide initiative called AI for Science to get these collaborations going. So in chemistry, seismology, neuroscience, all these areas, how do we use AI and how does it help also develop better AI methods? I won't again get into those details, but you can look at those works on my website. And then the last part, this is probably the hardest one because we now need our methods to be adaptive, right? So if we are going towards embodied AI, we need to design these adaptive tasks, but this is also going to be very hard to learn. For instance, if you want the robot not just to do backflips, but all kinds of different tasks, right? Like a human would do, or even a dog would do. how do we design benchmarks to see how well the methods do. And ultimately, like lifelong learning, it always keeps learning and learns new skills like some dogs do. How do we create benchmarks for that and good methods for that? I think all these are challenging aspects. So I just want to kind of lay out this wish list of where we would like to head with AI. Yeah, and like I was emphasizing throughout this talk, having inspiration from humans is so important. I mean, especially even babies can learn so well. I mean, and they're doing predominantly unsupervised learning, and they're able to grasp new concepts, right? The supervision only comes later when they are able to communicate and have a language to speak. But before that, it's all unsupervised learning. And this is so different from how the current deep learning methods work. So how can we take inspiration? And I think this is something that I'd be fascinated to discuss more with the community. Great. Yeah, so where do simulations come into play with all this, right? So I think of simulations as an example of the prior, right? So when we have only limited amounts of real data or the data in some domain, how can we create very authentic simulations, simulations that are close to the real data that can augment our learning methods? And how can we test also well in simulations, because now we have the control to design what kind of simulations we want and program them. So I think I'll emphasize in this talk on how some examples we can use simulations. The other aspects are, again, right, in some of my previous works, tensors are extensions of matrices to more dimensions. And we've shown in a number of works how this can help create neural network architectures that are better generalizable, that can incorporate multidimensionality very well, that can lead to compressible networks. And same with graphs, they can incorporate all kinds of interesting structures like molecular knowledge or right, social networks like this community thinks about. And I'll show you some examples of graph neural networks used to discover underlying causality in simulated models. So I'll give you some examples. And the other aspect of, is incorporating different known rules and laws, right? I mean, if I'm designing drones, I don't want to reinvent Newton's laws of motion, right? So they're already valid controllers, and we start there and we add learning to it rather than think of learning from scratch. We are not going to have an aircraft fly just from learning from scratch, right? So we want to use the current knowledge. So I think all these are some principles to design good priors. So a quick example I want to give is the NVIDIA Drive platform. And the idea is how we can simulate scenarios that, because we can't possibly have data to cover all the real world scenarios. And I can show a quick demo, and some of the work we've been doing at NVIDIA is precisely this aspect of how to generate at scale such scenarios and quickly test our policy and also find blind spots for the current policy. So let me see if this plays. That's the NVIDIA headquarters, by the way. And you can see this is such photorealistic simulation.
We can't only hear but not see. So we are still see only your slides. So yeah. So because Zoom has just share a screen, so you need to share.
Oh
the
yeah,
screen.
let me.
Yes. Yeah, that's the only. Yeah, that's
I forgot. Yes.
Yeah, the complication. Yeah.
Let me.
Just to share the new window.
Yes.
Yeah.
Yes.
Sorry.
Just trying to. Yeah, it doesn't seamlessly do that. here it is. Because each time I have to switch forward and back.
Excellent.
Yeah. So I already explained this. As you can see, it's highly photorealistic simulation. The pedestrians, you know, and we can have like physically valid friction models to make sure it's very close to the real world. And also, right, we can do nighttime and other weather conditions. Yeah, so like these challenging conditions, right? And we can look at how well are the current models detecting other cars in these challenging scenarios. Anyway, so that gives you an idea. And let me switch back to the presentation. Yeah, so that gives an example of how we can have a platform that combines both real data and simulated scenarios and test out, and also use synthetic data to create more examples. But there's going to be a domain shift between synthetic and real data. And some of the works we are doing is also asking how to handle such domain shifts. I won't get into the details here, but even again, that work you can look into my website. So another platform is the NVIDIA Isaac, which is a platform for robot learning, right? Like as I said, in our dream to have embodied AI, the role of simulation is so critical. So this is the example of the BMW factory, you know, the partnership we have with BMW. And what we did was created this digital twin, which is a physically valid simulation of the actual factory floor. And so now if you need to navigate around this, you can first do it in simulation and get a lot of headway through that. And the platform itself has other aspects like the EGX stack. So you can directly take from the cloud and from your trained model onto the real robots in a seamless way. So this is the other demo. Now let me, there is a little bit of this switching back and forth. Bear with me there. I wish I could find a more seamless way, but yeah, so this is the BMW factory, that simulation. So as you can see, you can simulate different kinds of surfaces and objects, right, obstacles, and how to pick and place. Yeah, and look at like how well is the pose estimation doing, how well is it able to pick up different blocks, and parallelize this on GPUs. And then you can do reinforcement learning. Yeah, and domain randomization is, so domain randomization is able to combine real data and synthetic data together. So that was another example. So now what I'll show is some work we've done using this NVIDIA simulators and using reinforcement learning to get very efficient walking behavior on different kinds of surfaces. So it's very much able to adapt to these scenarios, right? And this is what we talked about, multi-domain learning, that's important for putting these robots in the real world. Yeah, so what you can see here is that this controller, now we have it in simulation. This is the Leica robot, and there is a similar, copy in the real world, right? So there is a lot of physical validity we can create in Isaac platform, in the Isaac gym, and hence simulate different kinds of surfaces, different orientation, like kind of create all kinds of data in simulation, because in the real world, this would be too slow and too expensive to collect. So we can do this. And then the idea is we can employ reinforcement learning on kind of deciding how to mix different kind of, primitive set of actions, right? I mean, should the robot just stand? Should it trot? Should it pace? All these are examples of primitive actions. And what the hierarchical reinforcement learning does is to decide how to mix up these primitive actions. And so you can see here, it's kind of automatically learning how to mix up these primitive actions. And so start with first low speed so it gets to learn. And this is the principle of curriculum learning, right? And over time, it's able to adapt and learn even more challenging tasks. And we can test for robustness, for instance, like similar to a banana peel, like a frictionless surface. It's never been trained on this, so it's only seeing this now. It's, and if it was just the baseline where we didn't use learning, it would just completely fail, right? It's just falling off. But then the learned controller, where we use reinforcement learning, it's able to still overcome that. And so that's the idea, that it can do all kinds of impressive tasks. It's not just one task, it can do lots of different tasks because we can use reinforcement learning and train this in simulation. So right now, tests are underway to bring this to the real robot as well, which is delayed due to COVID. But we already have seen some impressive results of also bringing that. So these are some initial results of taking from the simulation to the real world with no other adaptation, right? So this is the bare bones, just directly take from simulation to the real world. And you can see that's already doing quite well. It's able to walk, it's able to get going and not fall off, so which is impressive. So it's able to do these tasks. And we also can test this kind of banana peel movements scenarios here, like look at, if you like now decrease the friction of a leg, or, kind of try to make it fall, how well can it hold up? And it's able to do that. And so that's the idea, that we can now use learning in simulations to effectively transfer to the real world. So yeah, so to kind of give an overview of this thread, what the NVIDIA Isaac platform provides is the ability to have physically valid simulations at scale, accelerated with GPUs, so that we can do large-scale reinforcement learning. This is extremely data-heavy method and compute-heavy method. But because we can do it in simulations, we can approach this problem and then take that to the real world. And even there, we are not learning from scratch, right? We are going to use all the existing controllers for primitive actions and only like do high-level learning to decide how to mix up those primitives. So these are all some principles to make robotics possible in the real world with learning. So that was one thread. So let me see how much time I have. The full screen, I can't like.
You still have 5 minutes, or even 10 if you need.
Okay. So I think I can kind of talk about this thread and think about causal discovery, because I know this is an important topic for this community, right? Because ultimately you want to ask for these kind of social network problems, what is the underlying cause for certain effects we see? So this is a work where we asked, can we do this discovery by using good simulations? For instance, if we have very realistic simulations of cloth and we see videos of, we generate such videos of cloth simulation, how well can we discover the underlying physics of that? And so once we do it in simulation, again, we can take it to the real world and enable such understanding of the physics of, say, real world cloth and other soft body objects, and ultimately use robotics to manipulate, right? If you want your robot to fold your clothes, you would need all this. But yeah, obviously there's lots of other important applications beyond the more mundane cloth folding. And yeah, I mean, that's again, like the question is, there are lots of physical systems we can simulate well, you know, rigid bodies like different, like balls just bouncing, right? Or like, as I said, cloth and other kinds of objects. And what they involve is certain key points, right? So these are like kind of essentially points in the surface where there is interaction, and you can model these interactions using a graph. Right? And that's when you can ask, how do I discover what are these key points and what is the form of interaction between them? So can I discover this causal graph? And how do I do this with visual data, which is very high dimensional? You know, if I now have videos of this with lots of pixels, how do I get that to a small enough graph that I can reason about the interactions and discover causality? So that's the problem we wanted in this talk, and in this work rather, right? The key aspects is there is disentanglement here. How do we get a good disentanglements, right? And how do we discover these key points, and how do we learn the graphs between the key points? And that's the idea here, right? And you can see the result of this. So what we did was we used key point detection methods, and then we used graph neural networks to train in simulation. This is the NVIDIA Flex simulation. It's the same simulation that's also was used in the earlier robot example. So we can utilize these simulations to predict the key points. And once we predict the key points, we can ask, how is that going to evolve in the real world? And you can see that it's able to predict and these complex movements of the cloth. And it's not just one kind of cloth, right? So it's not just the shirt, you can also do it, oh, sorry, I think I have to play it manually here. So different shapes of cloth, it can generalize, and this can only happen because we're discovering the underlying causality, right? So if you just did data fitting in a standard supervised learning method, you wouldn't be able to extrapolate to new scenarios. And that's what we see here, that you can have counterfactuals. So if you've never seen data like this, you can still predict what's going to happen in the scenario. For instance, if you change the length of the spring, right? Or in a kind of a rigid body scenario. Or you can extrapolate to many more balls than what you initially saw in your training data. So all these are possible because we are discovering the underlying causality. Without that, we wouldn't have extrapolation or counterfactual reasoning possible. And so that's kind of the challenge we had here in terms of how we can now use graph neural networks to infer these interactions. So the key assumption here is we can have data on many different configurations, right? So we have like cloth here in the form of a shirt. We may have like shirts of different sizes. So when you see many different configurations, then you can ask, what is the underlying physics that is the same in all these scenarios, right? And that's like a meta-learning problem. And if you use the same graph neural network to predict in all those configurations, it's forced to learn the underlying causal model. And that's how we can ensure good extrapolation to new scenarios. So another example is asking how we can get disentanglement learning and have that in style GANs. So as I said, I mean, we're creating all these simulations when we know the underlying physics, right? So I mean, robot, I know what are the Newton's laws of motion. I can look at the different spring properties. It's a lot of work. It requires deep expertise in controls and mechanics, but there are people who are doing that. But in so many other scenarios, we don't know how to even create the simulation. And that's where generative models are so important. And GANs, as I said in the beginning of the talk, have been great at generating new images so well. And so what we wanted to ask was, can we further disentangle different factors of variations and create more control in our GANs? And that's the focus of this work, is to ask, either input an image or, right, you can generate from scratch. But the important thing is the control, right? These factor codes, what it gives the instruction is, give me now, change this face to have an open mouth, right? So you could either edit an input image, or you can generate an image where the mouth is open. And this is important because now if you wanted to create the synthetic data with a specific property, we can. And what we saw was, if you have no labeled examples, so if I don't have data saying which of the mouths are open, it's very hard to learn this disentanglement, right? So because you don't have that supervision. So we wanted to approach the semi-supervised setting where you have some some labeled examples of when the mouth is open or closed, and can you then use lots of unlabeled examples together? And these are some details, I won't get into them, but the main important aspect is, right, so we have an unsupervised loss that encourages disentanglement, meaning images that have the mouth open and mouth closed should be disentangled, right? So you should kind of ensure that they are not close to one another. And when you have that supervised label, you can use that to further enhance the disentanglement. So this is some synthetic data we created to get good benchmarks for how we can vary, like lighting intensity, camera poses, everything, just learn purely from data, right? And also just very little data, just 1% of the data was labeled. And this is on the celeb data set where we have tiny amount of labeled data available. For instance, you want to put banks or add glasses, and that's enough to create these, very photorealistic images, but also enable control. So you can have both good images, good image quality, and also control over what you want to generate. And this is on new faces added, right? So these were not present in the training data. This is the editing scenario where you can edit an input image. And so the idea is, if you can add a little bit of supervision, that can go a long way in creating this disentanglement. Yeah, so I want to conclude now. Hopefully I've given you some high-level intuitions in terms of what it takes to create generalizable AI, right? And unsupervised learning is such a key part of this. And adding good priors is important. And simulations can be a great way to enable that. And we've seen examples in robotics where physically valid simulations can help us learn at scale and on the NVIDIA Isaac platform. And the other aspect I showed was causality, how we can enable causal learning using graph neural networks and give lots of different configurations in simulations using, again, NVIDIA Flex Simulator that can have these physically valid simulations. And lastly, I showed examples of controllable generation. When we cannot program the simulations, can we just learn to simulate from data? And that's where GANs are great at this. But if you want to add control to our GANs, we need to add some small amount of supervision, and that can go a long way to enhance them. Thank you.
Oh, thank you very much for this talk. And I just was monitoring the chat as a lot of questions. And I see 2 or 3 questions from Francisco, Gary, and others. So please, we have time, so we might, you can pose your question directly to Anima by just showing up your face and talk to her, yeah? Without me mediating and misinterpreting probably your point. So Gary, Francisco, would like to Bahid, you would like to say?
Okay.
Okay, go on.
I'll go first. So I'm Gary Polhill, and yeah, I was going to ask you if there were any AI systems that could learn how to game the system. So you know, if you have a set of rules, it would kind of learn how to kind of cheat, not necessarily sort of directly break the rules, but let's say exploit them to gain greater advantage than it should really have. So, for example, could an agent learn to commit fraud but not get caught, or could an agent learn how to get benefits to which the government maybe doesn't really want them to be entitled? Are there ways of doing that? Do you know?
So in a way, all the game playing parts are that, right? So, you know, if it's learning how to play AlphaGo, or I mean the Go game or any of the other games, right? So that's a set of rules, and it's learning to compete against other players. So that's the same principle. So the question is, how well can you model the environment to test this? So there is the AI economist effort, and that's in a way more for designing good policies. So it's more like kind of simulating good tax policies, for instance. But yeah, you could use platform like that to also ask, you know, if somebody is going to be committing fraud, right? What is the likelihood? So it all depends on, again, the availability of good simulation, right? And that's the challenging part, I guess.
Thank you.
Yeah. Thank you.
Rashira, do you have a question for Anima? Hope
Yes.
I not misspelled your name. Yeah, sorry in case.
Yes. Thank you for that very interesting and wide-ranging talk and all your wide-ranging work. So in one part of your talk, so for instance, the last part, you discussed generative adversarial networks for facial image generation. So that's an example of an adversarial learning where that's basically competition. And on the other hand, in your curriculum learning, the curriculum algorithm is essentially cooperating with the agent that is learning. So I have two questions. One is that there's actually a range in game theory of different things in between adversarial and cooperative learning. These are sort of extremes. So I was wondering if you had tried combining those. And the other is that games with 3 players are fundamentally more complex than games with 2 players. And I was wondering if that has been incorporated into these kinds of, they're kind of very, very basic social learning algorithms, social teaching of the AI algorithms.
That's right. Thanks, Ruchira. I think that's a great set of questions there. And I think I said in the talk that multi-agent learning is still very basic, right, in the deep learning community. And indeed, like, you know, the generator and the discriminator example is a competitive game, right? It's a zero-sum game. And people have been starting to think of some coordination games, like have multiple robots. Like, for instance, we are looking at bimanual manipulation. So if there are 2 arms, how they should coordinate with one another. But in terms of like the optimization method itself, we have recent work called competitive gradient descent, or CGD. The work is available on my website. And what that enables is, you know, in all these general scenarios, you don't have convexity or concavity, right? Like what more traditional game theory looks at. And so the question is, what are good optimization methods in such scenarios? And what we've seen is changing just simultaneous gradient descent to incorporate a part of the higher order term, like the mixed Hessian term, and still maintaining good computational efficiency. it enables us to capture the interaction of other players much more effectively, and hence stabilizes the optimization methods. So meaning, right, you don't have these wild oscillations we see sometimes in training multi-agent systems. So that's from the optimization perspective, and I believe in many of the games that can be much more effective.
Very interesting. Thank you.
Yeah.
Okay, thanks for also the intelligent questions. So we have Vahid. Would like to share your question with Anima, please?
Yeah, I'm here. So thanks for the talk. It's like a bit abstract question, not too technical. So in most of the examples, we saw that how simulation can benefit AI. So how AI systems can learn from simulation. Do you see any role like the other way around, how we can use AI systems to improve social simulation science?
Yeah, and that's where, the last part of my talk using generative models, right, I think is very valid, because you want to kind of almost have this loop, like start with simulations, try to take it to the real world, right, have some good domain adaptation methods, and then maybe also look at how much is the domain gap and further improve the simulation. So it's like sim to real, back to sim, right, that loop. I think ultimately we need to design those mechanisms, and we're beginning to do that. So some of the work from my colleagues at NVIDIA is looking at the sim to real, back to sim loop. I mean, not to improve the simulation, but just decide which simulation to select, right? Like what is the, for instance, if the spring constants are wrong, can you go and change the spring constants in simulation and train it again, or fine tune it and then go back to the real world? So in a way that's kind of, changing how you simulate. But if the simulation itself is having a shortcoming, it's going to be more challenging to improve that. But that's where maybe you can combine generative modeling with simulation to do that. I think that's a great question.
Yeah, one other question that's also like others are discussing in the chat is like this kind of doomed scenario that we will have a kind of general AI, and like it's more intelligent than us. And then we have this discussion of Stuart Russell, that says, okay, we need new definition of intelligence. Instead of looking at a machine that's able to optimize its own goals, it's beneficial only it benefits us. So do you see any role for this kind of adhering to human values in your notion of generalizable AI?
Yeah, I mean, I think that's why it's very important to model the human behavior, right? So, and it depends what scenarios we are going to use this on. I mean, what kind of social impact, societal impact it can have, right? Like the face recognition example that I gave, right, is one of the sensitive ones. So how I think, right, it has to be end to end, like what is the application that we are going to design? Who is going to be the stakeholder? Right? What is the outcome if it's a wrong decision, right? What are the other redundancies built? And right now we are not thinking all that end to end, right? Because many times there are so many players in the process as well. So, and there's so many subcontractors and so on. So by the time you see the impact, right, the designer doesn't know. But hopefully, I think more awareness of the presence of bias in these data sets and in the AI models will help us overcome that. But I agree, that's a challenging one.
Thank you.
Thank you. And there's also Francisco who would like to pose your question.
Yes, thank
Please.
you. Hi, Anima. This is Francisco from Madrid, Spain. I was wondering, I'm a little bit concerned about the natural computing type of models, how they can contribute to understand or inspire the behavior or simulate modeling and simulate human behavior, right? I'm talking about swarm intelligence, artificial immune systems, cellular automata, all that type of things. And I was wondering to what extent this is a line of work for you, or you just you are not focusing on that type of things. I mean,
Yeah, so, so some of my colleagues at Caltech are much more, going in depth in those directions. For instance, one question is, can we create good swarm of also artificial drones, right? And, birds can fly so close to one another and not, in fact, they use the aerodynamics, right, in a very effective way, even in groups to fly well, have those formations. And currently the drones are not able to do that. So some of the work there is looking at how to kind of have better learning to adapt to aerodynamics, even if there are other drones flying nearby. But more generally, if you ask about simulating some of that swarm behavior, right, the question is, I think there are some underlying rules that we can write out and we can simulate it. But the question is, can we then further have some data-driven methods to create better adaptivity that we see in the natural world? I think this is a great question. Maybe, it's not many machine learning people are looking into it, mainly because the data is not available, right? So if we could give lots of examples of swarms in the real world and also have that goal-directed behavior, right? So usually it's swarm of ants, they're going and kind of trying to find food. So I think those list of behavior and maybe looking at real videos, we can use the current deep learning methods to get useful behavior beyond the simple equations that we typically write out to demonstrate swarm behavior. But yeah, it's an open problem. I'm also curious to hear, everybody's opinion here on where we can go with that.
Thank you.
Yes, and perhaps Christopher could add anything, something. Chris, would like to pose a question?
Okay.
Yeah, please.
Yes. So Gary asked you about AI learning to cheat, and we were trying to think of an example of this, and I thought, well, going back to the self-driving car, what if we tell the car our goal is to get from A to B safely, but as quickly as possible? Could the self-driving car decide the best way to do that is to break the speed limit or to jump over the traffic lights, providing it's safe to do so? Or even perhaps decide that the biggest threat to doing it efficiently is human beings. So eliminate the human beings, like Hal in the film 2001. So I leave that with you.
So the first two examples were just leading me to say we have to build an Italian car. So put some Italian attitude about breaking the rules.
Or Indian, right?
Then you made the example. Then the third example was too tragic for an Italian.
So yeah, I mean, I think it all depends on how we, that's why we need regulation. We need all the testing, right? So that's why I feel like even right now, there is hardly any regulation and, it's dangerous. Like, that's why I don't own a Tesla. I would never trust to sit in a Tesla with autopilot on. I just don't, right? Because I know it is not ready. So we need mechanisms to incorporate all these scenarios, right? So, and have lots of other redundancy to ensure and lots of testing. And we've barely started.
Okay, thank you. If anyone else would like to pose any further questions, I will, given the power that the chair has, I will pose a couple of questions myself. Okay, so I've learned a lot in this talk, and so for instance, I just, for instance, we have pretty quite large data set about, for instance, real behavior of real subjects in lab experiments, a sequence of, for instance, decisions made by an individual in a type of games, like, game theory, like inspired games. So, and what typically we do is just to understand how those subjects have concretely behaved in a sequence of complex iterative games, or having an optimizing kind of theory driven like the economist in mind, and so observing that the discrepancy between the mismatch between the optimization that the theory will have dictated people to do and current behavior that they concretely do. So, and I don't know, maybe I for the sake of, I mean, for the knowledge, maybe probably someone has done or is doing it, would be nice to have this, to see this kind of data set without this kind of theory, optimization theory in mind, and without just looking at the concrete behavior of people, but having a kind of, you know, algorithm learning how people should have behaved concretely to maybe win the game or to do probably better. And then using this kind of, this is an example of probably your type of approach to be used in real, with social science data. So I really like that kind of example. However, the problem is I see is that whenever you learn something from your simulation models and then you implement this into a robot and you see, I mean, how the robot does that, the problem with the society, and whenever we learn from the simulation something that could be done, then we can't inject or implement that into a real social system, because in most of the case, these kind of decisions are political decisions. So
unless you're Twitter or
unless
Facebook,
you are,
right?
yeah, unless you are the king of an empire, yeah, of course. There's a little bit of complication whenever we try to, you know, show or inform a real concrete decision in a social system from simulations, even probably when these simulations are very robust and they probably have found something very, very important to do, then the fact that there's a political cost on doing this, so it's a little bit complicated, this kind of back and forth between simulation and real implementation, which is a little bit complicated. Yeah.
Yeah, I mean, I think that's a great question, right? How do we do this? I think what we need is an open platform, social media that's not in the hands of some of the big companies, right? So the question,
yeah, that's not it.
And then like open it to researchers, like how the internet was. Maybe I'm, you know, too much of an idealist, but we need to kind of create a new platform that where, you know, there is, first of all, better troll and other kind of behavior is checked and controlled and moderated. And maybe it's an avenue for research. So yeah, honestly, other than something like that, I don't see a way out. But maybe that's what this community, maybe can think more and join hands and create one like that. Because we need Internet 2.0, right? We need the next generation. And I feel like it needs to be built with a new foundation where the social aspect is embedded. I mean, when the internet was created, right, no one thought about the social aspect. It wasn't designed. It was designed for a few universities to connect together.
Okay, I will just to close with two questions. It was just so if you think about a community of people modeling a complex social systems, so modeling typically the emergence of social dynamics at the macroscopic level from simulating interaction between agents, and these kind of agents, humans are heterogeneous, different, and this kind of stuff. So what do you love to have for doing your job from this community? So what this kind of challenge that the limitation that you see about the type of you know, knowledge about human behavior that you don't have, that you will love to have to build better technologies and better systems in general?
I think one is the data sets, right? It seems like it's very fragmented, right? So it's somebody like me, outsider to the field, I can't kind of easily get the lay of the land and say, okay, this is a big data set, but this has this limitation versus the others. Whereas a lot of machine learning data sets are now very standardized, you know, and there's kind of a lot written, both of its advantages and its limitations, right? So I think opening that up to also outsiders like me, right, we can kind of say, okay, and these are, and also all the different models, like good surveys that would help, I think, more people get into the community. And ultimately, like maybe, right, like a platform or a simulation system that kind of incorporates the best of all the models, right? So like a package that, you know, right now, if I want different deep learning architectures, I can go to PyTorch, I can go to fast.ai, right? I can learn and kind of change the code quickly. So we need some repository like that where you can easily just change different models, different.
Yeah, it is a very good point. This is something that is around in our community since decades, about the challenge of building, not prototypes, but model architecture. That's okay. If you need to model human behavior in that domain, go for it. That's it. This is what, and so to build this kind of architecture in which, but it's something that's it's incredibly complicated, and especially when you have to really, put some confidence on the fact that human behavior is exactly this. You can go, okay, don't worry. Humans behave in that kind of way, in that kind of domain or context. It's something that is a little bit probably challenging. But yes, this is something that we discussed quite a long time, obviously without ending up with any kind of problem. But this is something that is it's part of our discussions. You touched about a kind of important point. So I would like just to explore your presence, just two last questions about it. If you remember, the topic of the social simulation conference, which was ideally now in Milan in a nice place, and was about also how to increase women participation in the field of, in this case, social simulation on age-based model, but in general in academia, especially in fields in which there's a kind of strong mathematics computing background. Well, I'm just happy to tell you that among the number of registered participants to this event, we got something like 60-40, 60 men and 40 women and other categories. So we were not dramatically, it's not dramatically, but obviously if you have any suggestion about or any I'll be briefly, I don't want to take you here take you hostages, keep you hostages for 2 hours, but just if you have any kind of message that you want to pass to our community about suggestions about how to improve inclusion and diversity in our community from the point of view of your career path and your experiences, that will be very, 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 very valuable.
Yeah. Thank you, Flaminio, for bringing that up. This is close to heart, and if you follow me on Twitter, like some of you do, right? I try to, keep the awareness on these issues, and especially how that closely relates to the AI bias and ethics, right? Because I think the lack of representation in the AI community has been a direct reason for creating such flawed models and launching them in this move fast, break things ethos of Silicon Valley. So I feel the social simulations community, and more generally sociology and in humanities, right? There is much better representation, and I think it has to do with not just take the approach to move fastest into something and not test very carefully. So all this is interconnected. I think having good, not only gender balance, right, in terms of race, age, ableism, like all these are issues that we want to ask how to enable everybody in the world to participate. So what I call democratization. So in fact, I would pose the other way. I think we have a lot to learn from your community to improve conditions in AI, because it's far worse. It's not just the numbers, the culture as well has to change more. And it's changed for the better in the last few years. If you followed the NeurIPS name change controversy, that demonstrated how much toxicity there is in the community. I've gotten like death threats and all kinds of things for proposing to change the name of a conference. So, we have a long way to go. And I feel like, we almost need better humanistic education of people in the tech community, right? I feel like they're so driven in a one-dimensional way that they're missing this bigger picture. And that's why I think, understanding human behavior of also that group of people and why there is toxic behavior and how we can change people's minds and hearts is so important.
Okay, thank you for the answer. Very, very brilliant. And I also like to thank for your counter-gender typic role about that you're playing in an environment which is not probably easier, and so keep going on. So it's very important for especially young women to have this kind of counter-gender stereotypic roles, and you're doing very well. So, Anima, thank you very much for accepting our invitation, and I'm sure that we will make your presentation public, and there will be a lot of people more than today, which is an uncomfortable hour time slot for many Europeans. And so I'd like to thank you for accepting our invitation, and for you did your best to try to contextualize your own experience in a new community, and this is very valuable, and I really appreciate everyone. So, and I hope to cross at some point our steps, and to meet you at some point, and I will continue to follow your research. It's very brilliant, and thank you very much.
Thank you. Thank you.
Whenever you pass by in Italy, please send me an email, and
yeah,
okay.
No, I'd love to, and there's so much I have to learn from this community, and I've started looking at some of the works in this conference. So thank you.
Okay, thank you very much.
Take
Bye.
care.
Enjoy your day.
Ciao.
Yes. Ciao.